Hi guys, welcome back to the channel. Today we're going to be talking about complex numbers. This is a recording from TrinMathCamp, which happened over the summer, but this is an abridged version. We edited it down. If you want to watch the full version, click the link in the description. I also wanted to let you know that if you have any questions at all, please feel free to comment them and we will totally respond. And then if you like this video and want to see more like it, go subscribe down below. Alright, let's get into the video.
So today's about complex numbers. It's definitely a very big field, so we'll try to introduce you to it. So before we get to complex numbers, let's talk about numbers that we actually understand first. So the real numbers, that's probably the numbers that you've worked with for basically your entire life. So and when you think about visualizing the real numbers, you do it on something called the number line, right? You just draw this line and it extends infinitely to the left, infinitely to the right. And then if anyone tells you a real number, you can just write a dot or point at it or something. You know where it is on that line. So if I told you 3, you could easily just point to 3. And then as you can see, 5 and -5 are dotted. And the reason that you can represent it on a line is because real numbers consist of just one component. So that might be a little bit of a weird concept to wrap your head around, this idea of one component, but that definitely will make more sense later. So what I mean by one component is that if you're told just one piece of information about a real number, so if I told you like 7 or 7.5, you would know exactly where on this number line to go to. But sometimes you need more than just one piece of information. By piece of information, we call it component. So an example of this is the plane. So I'm sure if you've had any experience with geometry, you've probably seen the plane or the coordinate plane. I think some people call it the Cartesian plane. So the plane, this is kind of the formal mathy way of writing it. So it's called r squared because each set element of the plane consists of 2 real numbers. So that's why you have the squared there. And it's basically made up of ordered pairs. So you can think of these as points, right? And then each element of the plane, it can't be described by just one component, right? If I told you 1, you can't point to anywhere in the plane. You would just ask me if I'm crazy. Like, you can't just be told 1 and then try to find 1 on the plane. So what you need is you need more information. So if I told you 1 and 2, or in math, we just write this for shorthand, 1, 2 in parentheses, like a point, then you can point to a very specific point of the plane. Out of all the elements there, there's just one that satisfies 1, 2, and then it's placed right here, so you can see that we can point to 1, 2. So this is just getting at the idea that each element of r squared, or in other words, the plane, consists of 2 components. So I'm sure you've heard this before, but there's the x-coordinate and the y-coordinate. And that's why we need a 2-dimensional object, the plane, to visualize it, right? You can't think of the plane in a line, right? You need that second axis to really think about and visualize these points. So this notion of 2 components will be very important for us going forward. So just another example of something with 2 components, but now instead of something geometric, now let's consider actual numbers. So if you haven't been exposed to complex numbers and you've probably just been dealing with, integers, rationals, like fractions, or maybe real numbers, those all really just have kind of one aspect to them. So there's this thing, it's looks a little fancy. It's called, it's read out loud, z adjoin root 2, or z brackets root 2. And then this is, I guess, the math way of describing that set. But I think a more intuitive way to understand this is really just that what this set represents is all the numbers of the form a plus b root 2, where a and b are positive integers. And the reason that this number has 2 parts is you kind of have a being the rational part, so that's just a pure integer, and then this is your irrational part, right? Multiples of root 2. So that's just what z adjoined root 2 is. And now let's get into why do we care? What's important about this set? So as I said earlier, before we saw a geometric object, the plane, whose elements had 2 components, but now we're seeing an example with numbers. So again, just to reiterate, this is the rational part and this is the irrational part. So even though it's just one number, you kind of have these 2 different number systems pushed together into one thing to form just one type of number. So you take the rationals, you take the irrationals, you just slap an addition sign on there, and then you kind of get this number that has 2 components. So again, just to go back to that example of I cannot just tell you 1 and then you would know what number I'm talking about here, right? If I told you 1, do I mean the b is 1? Do I mean the a is 1? Is it just root 2? Is it 1? Is it 1 plus 1 root 2? So you need 2 pieces of information, right? I'd have to tell you 4 or 5. And then you know what I'm talking about. Then you know I mean 4 plus 5 root 2. So again, you need that 2 pieces of information. What is the square root of -1? So let's think about, we're first going to ask ourselves, why do we care? Like, why are we asking ourselves that question? So just going back to a couple days ago when we were looking at inequalities, if you remember how we proved AMGM, we used, at least for 2 variables that is, we used this property of the real numbers, right? We said that any real number squared is non-negative. So if you take -1 squared, you get 1 positive. 5 squared, you get 25 positive. 0 squared is 0, so that's the only time it's non-positive. So that's why we write non-negative. And then sometimes this idea is known as the trivial inequality. And this kind of leads us to the question, okay, so then how do we square something and get a negative number? Or in other words, what is the square root of -1? What is the square root of negatives? So we know it's not a real number, right, because of the trivial inequality. So what we do is we define it to be a number called I. So let's get into a little more about I. So the definition of I is that it's a number such that when you square it, you get -1. So the answer to that question, what squared is negative or -1, and that answer is I. And just a little bit of terminology. So we call 1, 2, 5, 6.7, we call them real numbers. I is called an imaginary number. So just a little bit of terminology, and again, that's why it's called I for imaginary. So now just a little bit more about I. So we're going to try raising I to some powers. First we have I to the first power. So that equals I, because anything to the first power is just itself. Then I squared equals -1 by definition. That's just how we defined I. Then for the third and fourth example, we have to be a little bit more clever. So for I cubed, we can break that apart as I squared times I. And then we know I squared is -1 from the example above. And then -1 times I is just -I. And then a very similar strategy for I to the fourth power. So I to the fourth is I squared times I squared, which is equal to -1 times -1, which is equal to 1. Let's move on to complex numbers. So earlier we saw this theme of kind of taking 2 different numbers and then merging them together. So that's kind of what complex numbers do. What they do is they take the real numbers, they take imaginary numbers, and then they put them together. So we'll just write the formal notation, and then of course we'll break it down. So the complex numbers is denoted by a C. So in the same way that the rationals are denoted by Q, integers by Z, real numbers by R, complex numbers are by C. Hopefully that should make sense with the C. And they're equal to A plus BI, where A and B are real numbers and I squared, this is just the definition of I. So as you can see, they have this real part called A, and then the imaginary part is B. So oftentimes we've talked about how to visualize these numbers. So for example, with the real numbers, we visualize them in the number line. But for complex numbers, we need a plane. And the intuition for this maybe is perhaps coming to you is because that complex numbers have two parts, right? They have the real part, which is the A, and then the imaginary part, which is the B. So 3 plus 4i, you can think about it if you just want to plot it and kind of get to a place that feels comfortable for you. You can think of 3 plus 4i as like 3 comma 4 on the plane. So now let's talk a little bit about the algebra of complex numbers. How do they add, subtract? Anytime you work with a new number system, it's a good idea to think about how do the things you learned previously translate over to this new area that you're working with. So the good news about complex numbers is that they're very, very intuitive. So they kind of work exactly how you'd expect them to work. Here you have a plus bi plus c plus di. Let me just amend an error I have here. So the way it works is that you add the real components, and this should be a b, because we're adding the imaginary components. So basically what you do is you take the complex number, you can think of it in just its two separate parts, the real and the imaginary. Add the real, which is a and c, add the imaginary, which is b and d, and then you have your addition. Subtraction, it's really the same thing. And again, remember that the c is actually a b. So what you do is you take your real part, subtract by the other real part, and then you take your imaginary part b and subtract by your other imaginary part d. So you have a minus c plus b minus d times I. Multiplication. So this looks more complicated, but it works exactly how you would like FOIL, so to speak, if you've ever heard that. So you just distribute everything. So I didn't write out all the terms here, but I can just walk everyone through it to see how we get to the final step. So first you can do a times c, so that's ac. Then you do a times di, so that's ADI. Again, I know I said it earlier, but I really want to stress that I is not a variable, it's a number. Then you would do BI times C. So that's BCI. And then this last step is a little bit tricky because you have BI times DI. But if you take the i's and multiply them together first, if you remember, I times I, or in other words, I squared, is -1. So BI times DI is really negative BD. So that negative coming from I squared equals -1. And then we just group the real parts and the imaginary parts because that's how we like to think of our complex numbers. And then you can see all these numbers are in our explanation here. So again, sorry about all the arrows, but the main idea I'm trying to get across here is that complex numbers, if you want to multiply them, just distribute everything and it'll work out perfectly.
Right. Now, I would also stress the way Akash is doing here, like he's basically grouping the real and the imaginary parts. Like that'll become very, very helpful just going forward. Just trying to like group your imaginary parts and your real parts together.
Yeah. Yeah, so definitely always try to think of your complex numbers in terms of the real part and the imaginary part. All right, so I'm just going to move on to division. So division, it probably won't come up as much. So if you understand addition, subtraction, multiplication, that's already great. But we'll just talk about division very quickly anyway. So if you have a complex number divided by a complex number, it's not immediately obvious that that's another complex number, but it is. So what you do is you multiply by the conjugate of the denominator. So just a little terminology, the conjugate of c plus di is c minus di, or the conjugate of a plus bi is a minus bi. So you just take this plus and you change it to a minus. And then what's really cool about this is that if you multiply these things out, the denominator actually becomes c squared minus d squared. And the reason we like that is because the thing that was annoying us in division is how we had an I in the bottom. And we really want that. We just want the I on the top. So
I believe there's a little bit of a typo. I think it should be c squared plus d squared.
oh, sorry about that. Yeah, so then it would normally be c minus because the difference is squares, but remember that I squared is -1, so it changes the negative to a positive. It's a little bit hard because you have two components. What does big mean? So there's this thing called magnitude. So I'll just give the formula first, but there's a geometric intuition to this that I think is far more important. So the definition is just the square root of a squared plus b squared. We're gonna talk briefly about the idea of comparing parts, and then we'll get on to some interesting problems. So Foy has mentioned earlier that it's a good strategy to always keep your real parts together and your imaginary parts together. And this strategy really utilizes that. So we're just going to look at an example problem. So if you have x squared minus 2x, so that should be a real part, plus root y times I, so root y is your imaginary part, and then you know that equals -1 plus 2i, and you want to solve for x and y. So because the real and imaginary components of a complex number are separate, we can compare parts. So really what this is saying is that if you have two complex numbers that are equal, the real parts have to be equal and the imaginary parts have to be equal. So you can try to think back to the plane, which I'm sure you're more comfortable with. 2 points are equal only if their x coordinates are equal and their y coordinates are equal. So it's a very similar thing here. So just carrying out that strategy here, just to see an example, you would have that x squared minus 2x equals -1. And then if you solve that out, you'll get x equals 1. And you also have root y equals 2, which means that y equals 4. So the square root of -119 plus 120i can be expressed as a plus bi. So again, here we mean that a and b are real, and what we want to do is solve for a and b. So as per the first hint, you definitely want to square both sides. So when you square both sides, what you get is -119 plus 120i, right? If you take the square root and square it, the square root just goes away. And then the right-hand side is a squared minus b squared plus 2abi. So that'll look a lot like that if you've ever seen, x plus y the whole squared is x squared plus y squared plus 2xy. The one thing that'll look a little bit different to you is that there's a minus b squared instead of a plus. So just keep in mind that's because bi squared is b squared, but it's also times I squared, and I squared is -1. So when multiplying these things out, just make sure you don't drop any negative signs because the I can be a little bit tricky in that sense. So now the main part of this solution is the comparing parts, right? So as I said earlier, I'm just gonna box these. So a squared minus b squared is your real part, and then the coefficient of I, your 2ab, is your imaginary part. And then if we look on this side, 120 is your imaginary part, and then your real part is -119i. I'm sorry, -119. So as we said, complex numbers are equal only when both their components are equal. So we can equate the two. So we have a squared minus b squared equals -119, and then 2ab equals 120. And now we're not even dealing with complex numbers anymore. So what we've done is by comparing coefficients, we've taken ourselves back to some place that we feel much more comfortable with, just the real numbers. So this is just a simple system of equations in the real numbers. So now we can go ahead and solve it as you normally would by substitution. So if you have 2ab is 120, then that's the same thing as b is 60 over a. So you can substitute that into this squared equation. So b squared is 60 over a squared. So that's 3600 over a squared. Multiply everything by a squared. So the a squared becomes a to the fourth. This a squared goes away. So that's why you just see a 3600 here. And then this 119 times a squared. And and then there's a plus sign there just because we moved it over to the left-hand side. And then you can be a little bit smart about how you factor it. And then you could, by the way, if this factoring doesn't come naturally to you, you can just treat this as a quadratic of a squared. But just to keep things a little simple, you can factor this. And then keep in mind that a is real, right? A is real. So a squared plus 44 won't give us any solutions that we care about. So then what we have is that a is either 5 or negative 5. So a is plus or minus 5. And then if we look at how we define b, b is 60 over a. So 60 over plus minus 5 is plus minus 12. So we have two solutions, negative 5 and negative 12, and 5, 12. So another problem, again, very similar idea, just a little bit more difficult. You have a, b, and c are positive integers such that c equals a plus bi cubed minus 107i, and then we just give the definition of I. And the goal is to find c. And keep in mind that a, b, and c are positive integers. That's very important. The first step, as usual, is to expand out both sides of the equation. So first off, you see this plus 107i here. So we just added 107i to both sides. So that comes from this. And then if you work out a plus bi cubed, hopefully you get that it's a cubed minus 3ab squared. That's the real part. Plus 3a squared b minus b cubed I. So 3a squared b minus b cubed is the imaginary part. And then we just describe this notion of comparing parts. So the complex numbers are equal only if their real parts and imaginary parts are equal. So that's comparing parts. So this is how you know that c equals a cubed minus 3ab squared. So that's just comparing this real part to this real part. And 107 is equal to 3a squared b minus b cubed, and then we just factor out a b here. So that's just comparing parts. And now we kind of start to begin to use the fact that a and b are integers. And also, we should note that 107 is prime. So we know that b divides 107. It's a factor of 107 because we have this b here and 107 there. So b is a factor of 107, which is prime. So that means that b is equal to either 1 or 107, right? Because the only factors of a prime are 1 in itself. So now let's say that b is 107. Then we get that 3a squared minus 107 squared, right? This is just coming from over here, equals 1. So that means that 3a squared equals 107 squared plus 1. But then that means that 107 squared plus 1 is divisible by 3, but that cannot be the case. So this is, I guess, a little bit difficult to understand if you don't know mods, but don't worry about it too much. I can explain it that way. So if you do know mods, basically you can think of this mod 3. So what you should get is that 107 squared is 1 mod 3. This is 1 mod 3. So the whole thing is 2 mod 3, not 0 mod 3. And you can also just check for yourself, if you don't know mods, that this number is not divisible by 3. So now that we know b cannot be 107, the only other case we have left is that b has to be 1. So if you plug in b equals 1, then you have 3a squared is 108. So a squared is 36. And then that means a equals 6. And you might be wondering, why can't a be negative 6? Well, if we just go back to the problem statement, we see that they're positive integers, so it has to be 6. So then you use your equation for c when you compare the real parts. And that was a cubed minus 3ab squared. So then what you get is 198. But let's get back to this idea of multiplying by powers of I, because there's a lot to be said, both algebraic here, but also we're going to get into the geometric part of complex numbers, which is pretty interesting. So first, we multiply by the first power of I, 4 powers of I. So you might want to ask yourself, why 4? So you might want to think back to that time when we were raising I to some powers and the pattern we saw there. So just maybe think to yourself, why 4? So for the first case, 2 plus 3i times I to the 0. So I to the 0 is obviously just 1, and then 1 times anything is itself, so that case is not particularly interesting. Then times I to the 1. So if we multiply this out, we get 2 times I, so that's what you see here. And then 3i times I is negative 3, right? Because the I squared becomes negative 1. So then you get negative 3 plus 2i. Then you have 2 plus 3i times I squared. So remember, I squared is just negative 1. So you just multiply 3 by negative 1. So the 2 becomes negative 2, and the 3 becomes negative 3. Lastly, you multiply by I cubed, so it's a little bit more tricky. So you can remember that I cubed is actually negative I. And then if you do out the multiplication here, what you get is 3 minus 2i. So first off, just by looking at these numbers, you can tell that there's something going on, right? You start out with 2 and 3, and then it's, you get 2 and 3, then negative 3 and 2, then negative 2, negative 3, 3 and negative 2. There's some sort of pattern going on here, right? The 2 and 3 seem to be switching. There's kind of these negative signs that come and go. So it's maybe a little bit hard to figure out what the pattern is just by looking at these numbers. But if we plot them in our complex plane, you'll see the pattern hopefully pretty quickly. So if you put them on the complex plane, you have 2 plus 3i there, right? Because 1, 2, 1, 2, 3. Then you have negative 3 plus 2i, because you go 1, negative 1, negative 2, negative 3. And the plus 2i is 1, 2. And then same logic for these other two complex numbers. And then what you can see is that every time you multiply by I, you're actually rotating by 90 degrees. So maybe I can just draw in little arrows that'll make it more clear. So you multiply by I, and these are all 90 degrees, by the way. Hopefully you can see that. So these are all 90 degrees. And what we did here is you multiplied by I. And this process actually happens the same for all of the other terms. So that is kind of, you can already begin to see that complex numbers, they have a lot of great, algebraic properties, and they can help you in a lot of ways there. But they're also really cool to think about visually and geometrically. Complex numbers, I think one of the coolest things about them is that even though they're just numbers and you'd think that it's really just algebra, you just basically take a real number, define some new thing, I to be the square root of negative 1, but then it really just opens up this whole new way of thinking about geometry. So this is a rotation by 90 degrees, and we can also reason this algebraically. So we see this geometry with this example that's rotation by 90 degrees, but let's think about what this means in the context of what we said earlier in terms of raising I to the powers. So if we think about I to the 4th, in this context, it means that we're rotating by 90 degrees, right? So rotate 90. And then that to the 4th power. So if you think about what it means to rotate 90 degrees 4 times, like you can just imagine standing right here, rotating 90 degrees, then rotating another 90 degrees, then you'd be facing the opposite direction, and then 2 more, and you'd be exactly where you are. So rotating 90 degrees, hopefully you can convince yourself that that's the same thing as rotating 360 degrees, right? And then rotating 360 degrees is actually just the same thing as staying in place, right? 360 degrees, you'll just end up exactly where you were. So then you get that I to the 4th geometrically is the same thing as staying in place. But if you remember way back ago when we were lifting I to some powers, we saw that I to the 4th equals 1. So we can see both geometrically and algebraically, we can figure out that multiplying by I to the 4th essentially does nothing. So you can think about rotations, rotating 90 degrees 4 times does nothing, you stay in place. Or you can think about it algebraically. If you work out the numbers with I to the fourth, you'll get 1, and multiplying by 1 does nothing. So you can kind of begin to see there's this relationship between the algebra of complex numbers and the geometry of complex numbers. And then just a quick note, so you can think of I as having to do with rotation. So we saw it rotates by 90 degrees. And then just to think about what this means for the real numbers, right? Because complex numbers have 2 components. Multiplication by -1, essentially what it does is it reflects. So if you start at -3 plus 2i and multiply by -1, you reflect and you get 3 minus 2i. So part, and geometrically they kind of have this reflect and rotation part. So that's a little bit harder to grasp, but just wanted to get that sort of geometric intuition going. And then we'll just briefly talk a little bit about some more geometry stuff, and then that'll enable you to solve some really cool geometric complex number problems. So first, there's this idea of the polar form of complex numbers. So you may or may not have seen polar coordinates in a math class in your own middle or high school. But if you hopefully know some trig, if not, then this might be a little bit difficult, but if you know some trig, you can see that if you have this angle theta, and you know the distance is r, so in other words, the magnitude is r, then this is actually a whole new way of representing your numbers, right? So instead of its x coordinate and y coordinate, you can think of each number as an angle. So this angle, we always do it from the x-axis just by convention, and then its distance from the origin. And then we can set up these conversions that are somewhat useful to us just with some tricks. So you can see that this length, which we typically denote by a, we've been having this as a, and this part being b for the a plus bi. So it's actually the same thing as r cos theta. And the b is actually the same thing as r sine theta. So then we can think of a plus bi as r cos theta plus I times r sine theta. And most of the time we just factor this r out. So we have r times cos theta plus I sine theta. So these are just some conversions. So as you can see, the x coordinate a is r cos theta, the y coordinate b is r sine theta. This hopefully will make sense to you just because r literally is just the magnitude, radius is magnitude, and this is how we define magnitude. And if you're not okay with the definition, feel free to just think of it as Pythag. And then sometimes it's useful to figure out what theta is. So you can see here that tan theta opposite over adjacent. So you have tan theta is b over a. So if you want to convert to polar form, essentially you need 2 things, right? For rectangular, you need a and b. And for polar, you need r and theta. In other words, you need the magnitude and the angle. So for the magnitude, remember that it's equal to a squared plus b squared, the square root of that. So you get it's the square root of 3 squared plus 4 squared, which is 5. And then this angle, it isn't very nice, but tan theta is equal to 4/3. So theta is equal to tan inverse of 4/3. And then you can plug that in into what z should be. And this may look really kind of weird, but this tan inverse of 4/3 really is just theta, it's the angle. So it might be a little bit simpler just to think of it as the angle. And then there's this notation called cis. So when a lot of the time you have cos theta plus I sine theta, and that's a little bit annoying to write out all the time. As you can see, it's getting pretty long. So cis theta is the same thing as cos theta plus I sine theta. So you see the C for cos, the I for I, and the S for sine. So that's just shorthand notation. So we'll just go through this, and then after you understand this, you should actually be able to solve some pretty interesting problems. So this looks a little bit weird, but let me just try and break it down. So you have 2 complex numbers. So this is the magnitude of the first one, and then this is the angle of the a first complex number, and likewise here. And you're saying that if you multiply them, you get this really weird looking equation. But if you think about what it really means, you're first saying that the magnitudes multiply, right? So what I mean by that is you take R1 and R2, the two magnitudes, and your magnitude of your new complex number is just the product of your old magnitudes, right? You take R1, R2, and multiply them. And then if you think about the angle of this new complex number, you're just adding the two angles, right? So you have theta as your old angle, alpha as your other old angle, and your new angle is you just add them together. So equation-wise, this looks a little bit abstract, but if you just think about what it means geometrically, you're just saying that the magnitudes multiply and the angles add. So
I was going to add, just like this, just having this intuition, like if we go back and think about when we were multiplying 3 plus 2i by I, you can see like the magnitude essentially of what we're multiplying is what we're multiplying by is I. So I has magnitude 1, and so that's kind of the reason why like our 3's and 2's stay, because our magnitudes are staying the same.
Right.
And the idea of our angles adding is essentially we're adding 90 degrees.
So this is just saying that if you take a complex number and multiply it n times, the magnitude just multiplies n times. That's why you see an exponent. And then adding something n times is just multiplication. So you see that n theta there. So showing that angles add and magnitudes multiply. Now that we know that angles add and magnitudes multiply, this computing 1 plus I to the 12th power, while before we might have just expanded everything, that we probably don't want to expand something 12 times. So this is the polar form. So the magnitude of 1 plus I, if we plot it on the plane, would be root 2, right? So if we put it on the plane, it would be around here. So then this part is root 2, because this is 1 and this is 1. This is root 2, and then you can obviously see this is 45 degrees, or in radians, we call it pi over 4. And then if we use the fact that the magnitudes multiply, then we get the magnitudes multiply, so it's root 2 to the 12th power, right? Because root 2 times root 2 times root 2, 12 times. And the angle adds, so if you add pi over 4 12 times, it's just pi over 4 times 12. Then we just simplify these things a little bit. So 2 to the 12th, root 2 to the 12th is 2 to the 6th, which is 64. And then pi over 4 times 12 is 3 pi. And then we can just subtract off 2 pi because that's just 360. So we get pi. And then pi, which is the same thing as 180 degrees, by the way, if you don't know radians. 180 degrees is, of course, here. So that's -1. So this is really 64 times -1, which is -64. So now with this geometric way of thinking about complex numbers, these giant computations, which before would take you a really long time to compute, now can just take seconds with just knowing that magnitudes multiply and angles add.
Thanks so much for watching. We hope you enjoyed. If you want to see more videos like this, either subscribe or watch some more videos on the screen.